you everyone for coming. Thank you to the organisers for inviting me. First time in Edinburgh, as people say. So yeah, I'm going to talk about diffusion models again. So this is, I think, the third talk, maybe fourth talk that we've had on diffusion models this week. Really good talks that we've had. And I'm going to be, similar to Robert earlier on today, be talking about a combination of SDEs and PDs in the context of diffusion models. And in particular, how the different dynamics we get from different generative processes defined by both an ODE and SDE vary from each other actually quite dramatically, even though in theory they should be quite similar. So yeah, I'll start with the obligatory, slide of pictures of people and things that don't exist. And I've been quite careful. You might think that these don't look as good as like the new state of the art for stable diffusion. I wanted to make sure these were generated by the score-based framework that I'm going to talk about. So if they're not as nice as your modern up-to-date AI samples, then I'm sorry, but I wanted to make sure we were accurate. So the outline for my talk is going to be, first I'll talk about the dynamics. So we've heard about these a few times already today. But then these sort of evolve into approximate dynamics, which I'll outline. And then I'll lead into where this gap comes from, what it looks like in some sort of toy examples, how we might be able to bound it, and then maybe we can use ideas that we learn in section 2 to come up with numerical things we can use to close this gap a little bit, although there are some quite big caveats. Okay, so theoretical model, what do we have? So we want to generate data from some data distribution P0. So what we do is we define P0 as the initial condition of an SDE. We simulate this SDE forwards in time, and you end up with a density that evolves over time. So I've got 3 toy examples. This is one of them. You'll see the other 2 soon. But you end up with dynamics that do something like this. Okay. And as t goes to infinity, then this converges to a stationary Gaussian, though you don't ever quite get to that stationary Gaussian. You can get really close, and this tends to be good enough, such that if you define a reversal of this SDE, which has this equation here, which was derived by this guy Anderson in the 1980s, then given this drift function, which involves the score function here, the gradient of log density, then you should exactly recover the density that you had going forward. So if you want to generate new samples from P0, all you have to do is to be able to sample from P of capital T, and then you run this SDE backwards in time. So these are the forward dynamics of an SDE that you run backwards in time, and this gets you a new sample from P0 or from PT for any value of T. Okay. And then, okay, so associated with this as well is another sort of generative process you can run, this probability flow ODE. And this thing can run, because it's deterministic, you can run it forward and backward. The equation is the same, you just reverse time. And so if you want to generate new samples P0, you again sample from your Gaussian distribution for some large T, and you run these dynamics backwards in time. Okay. So the key thing to know here is that all of these things, in theory, generate the same distribution. They all share the same distribution. But if you want to generate something new, you need the score function, gradient log of P of T. Now, okay, the problem here is we don't have the score function, so you have to skip the slide. So this I've stolen from Song. You'll probably see this name a lot. But this is like a nice infographic showing what's going on here. So the SDE dynamics can be shown by these wiggly lines. The ODE dynamics are sort of these smooth lines here. And the idea is if you want to sample from a complex data distribution on the left, you noise it forward in time with your forward process, and you sample from the stationary distribution in the middle, and then you run either the reverse SDE forward or the probability flow ODE back. Okay. So we want to generate new samples. So we want to run one of those 2 equations on the right-hand side. So the score function. We don't have the score function, so we have to approximate it somehow. And to approximate score functions, we tend to try and minimize what's called the Fisher divergence. This is just the sort of the 2 norm of the difference between the true score and some neural network approximation of the score. Now, obviously, we don't know this, so we can't evaluate this directly, but there are a couple of options, or possibly more options, that you can use instead. So this one here is called slice score matching, and you get it from just writing this expectation in integral form and integrating by parts. This one here is called denoising score matching. And in here, you don't actually need to evaluate the true score, but you evaluate the score of the perturbation kernel of your forward process. So that's the Gaussian kernel. So if you do know that, you can play with that. So the point is that you train a neural network, you minimize an objective of your choice, you get an approximation. Okay. Now you want to use this approximation to generate samples. So you're going to take this approximation as theta and substitute it into one of your generative processes. So if we think about the reverse SDE, then the generative process is this guy here, where I've substituted in my neural approximation to the true score. And you make another approximation that P of capital T is the stationary distribution, which usually doesn't do too much harm. But now this reverse SDE is just an SDE. This goes backwards in time, which means that you can reverse this and write down the corresponding forward SDE, which has this density. And it also has an associated probability flow ODE. So yeah, I call this the approximate SDE, and you can run it in reverse, you can run it forwards, although you can't actually run this. This is just the dynamics because you don't know the score of the density generated by the approximate SDE. And the same for the probability flow ODE. Okay, so here are now 3 processes, all of which approximate the true forward process, but none of which are the same. And the only one of these 3 processes that you can evaluate is this guy. Right. So what's our other generative process? It is, the probability flow ODE, which you run backwards in time. So you can do the same thing. You substitute your score in here. You can integrate this backwards in time, and you end up with some approximation, which I call POD here, to the true density over time. And for this, there are no, that I know of, associated SDE dynamics. This is an ODE, and that's the two that you get. So what started with sort of your theoretical model with sort of one set of dynamics evolved into, so I presented this in a slightly chaotic way because when I was trying to sort of put notation around all these things and give them names and things like that, it took a lot of work and rejigging, and we found it quite confusing. So I thought I should present it to you in a slightly confusing way, but not too confusing. So I went through to together. But yeah, so you have sort of your true model, which has these true dynamics up here, which go forward, backwards. There's a stochastic, there's an ODE version. You have an associated score. I haven't put it in here, but there's obviously going to be a Fokker-Planck equation there. You have your approximate SDE dynamics, which again have all the same types of dynamics as the true dynamics. ODE dynamics, and you also have this sort of neural approximation, which doesn't come from any dynamics, but it is an approximation to something to do with your density that you make by your neural network. You'll note here that I've put sort of my score approximation is the gradient of some neural network U. So I think this is easier to follow if you think about U as an approximation to the potential model, and take the grad of that to be the score approximation. But it works in general, by the way. Okay, so the talk is going to be mostly about how do we sort of make sense of these things, and in particular, how do these differ from one another? So there are some quite famous, well, there is a quite famous existing result, which is that thing at the top, which says that the KL divergence between P0 being the density that your target density that you want to sample from, and PSD being your approximate density, is bounded by the KL divergence between, so the difference between a true Gaussian and the density at some final horizon t. So you're converging to a true Gaussian with increasing t, but you never quite get there. So that term tends to be quite small, but it's there. And the second term is the Fisher divergence, so the score matching objective. And then the second result, which is for the ODE, is not very well known, but I think it's a nice one to present because if you know this one, you're familiar with the literature, then you can look at this one, you can sort of see what's going on. So the first two terms here and here are the same as those two terms. But you also have this diff term. And this diff term is not very nice, but it basically tells you how does the KL divergence between ODE and truth differ from the KL divergence between ST and truth. And it involves two terms, so the product of two terms. One here is, again, the term that pops up in your Fisher divergence. But this term here is the discrepancy of your score model from the density that the probability flow ODE generates. And this isn't very easy to make heads or tails of. It's not clear whether these two vectors point in the same direction or in different directions. Is this increasing the divergence or is it decreasing the divergence? But that's what it is. And there's a lot of other works I haven't referenced that have looked at the differences between the scores generated by the reverse SDE. Sometimes they look at the discretizations. Some people looked at the ODE versus the truth. Some people looked at the ODE with some additional Langevin steps. There's many variants of this type of analysis. Yeah, so while we can't sort of make heads or tails of this by looking at it directly, we can sort of investigate it just practically what comes out when you simulate these things. So these are so the top are some experiments that I've run. So again, those three data distributions that I showed you at the start. So I train a score model with one of those loss functions, and I sample using the approximate SD and the approximate ODE, and you get distributions that look like this. And so visually, it looks like this L-diff is having a negative impact. We're moving away from the data distribution that we want. Although I think in sort of high dimensional settings, if you were working with images or something like this here, you might not notice because all of these samples are in high probability regions. They'd probably be quite convincing images. But if you look at the underlying distribution, you can see there's clearly a difference here. And again, this table at the bottom is some results. So these are FID scores for the two models trained with the same score model. And yeah, in the literature, the same thing has been found that the ODE does worse than the SDE in most cases. So should we just use SDs? In most cases, the answer might just be yes, but sometimes there are good reasons to want to have an ODE. For example, if speed is a concern, you might have faster optimized integrators for ODEs than you have for SDs. And there are some applications of this deterministic method. So maybe you want to interpolate your latent, so maybe you want to solve an inverse problem. You need to be able to deterministically map from some latent value and the Gaussian distribution to a data. Okay, so the angle that sort of I came at the start, or we came at the start, is instead of comparing the SDs to the ground truth or the ODs to the ground truth, why don't we just compare the SD ODs and see what we can come up with? And our sort of motivation was that you derive this probability flow ODE just by reformulating the Fokker-Planck equation. So if you've got a Fokker-Planck equation up here for the forward process, all you do is a few lines of algebra and you move this diffusion term into a drift term. And so you can look at this as, you know, a Fokker-Planck equation with zero drift or a transport equation. But either way, you end up with a deterministic flow of your probability mass, which you can describe by an ODE. And so the conjecture is that since this is how you come up with sort of this probability flow ODE, then the gap between the SDE and ODE distributions should somehow be indicated by some error in this Fokker-Planck equation. Okay, so we want to look at the difference between these distributions. And in particular, we want to look at how far is the distribution generated by the approximate ODE from the distribution generated by the approximate SDE. So the thing to consider here is not the standard forward or the true Fokker-Planck equation. It's actually the Fokker-Planck equation for the generative process. So Fokker-Planck equation for this approximate SDE. So that's what you see written up here. And it's slightly non-standard, this Fokker-Planck equation. Anyone see why it's different? So yeah, the slightly strange thing about this Fokker-Planck equation is you have negative diffusion here. So you've got plus where usually you'd have minus, but this comes about because I mean, it's the Fokker-Planck equation of dynamics that run backwards in time, but the Fokker-Planck equation is run forwards in time. But what's quite slightly counterintuitive about this is that it's also an extremely close approximation, or it should be, to a Fokker-Planck equation of your forward process, which runs forwards in time and has positive diffusion. So, but yeah, but this is what it is. You can derive this from the equations for the approximate SDE that I showed earlier. So you end up with this sort of feedback loop where the probability that you generate is determined by your score approximation being imperfect. But if you want to make the SDE samples close to the ODE samples, you want the score that you approximate to be consistent with the density that you generated. So one determines the other, but you want the other to influence the first one if you want consistency here. So the question that we're asking here is the score consistent with the distribution that it generates? And actually, to answer this, the ground truth doesn't matter to us. Like, this score approximation could be any good approximation of any Fokker-Planck equation. It doesn't have to coincide with our data distribution, and you would still get alignment between the ODE and SDE distributions. Obviously, in practice, you also want good samples from your data distribution. But in order to answer this sort of SDE-ODE gap question, you don't actually have to think about that. Okay, so how do we measure disagreement of between our score model and the Fokker-Planck equation? Well, you wouldn't do this in practice, but assume that instead of parameterizing a neural network for the score, we parameterize one for the density. And we just compute the score implied by that by taking the log and differentiating. Then you can write down sort of the residual as the Fokker-Planck equation that is implied by that. And because this P here is an approximation, this will be a non-zero quantity, but when it becomes small, that means that locally at least you should be satisfying the Fokker-Planck equation. And this is what people do with the trained physics and neural networks. They residuals and then they minimize those residual domains. And the point here is we want to satisfy the approximate SDE, but once you plug this neural approximation into the approximate SDE, then the residual ends up being exactly the residual of the forward SDE, which is nice because it means that we don't have to construct this if we want to evaluate it, but it's not important. We could construct both. It's just this one at the bottom is simpler. And then you can write down two related Fokker-Planck equations or Fokker-Planck equations of sort of transform solutions. So we call this one the log Fokker-Planck equation, which is the PD satisfied by the log of the density, and the score Fokker-Planck equation, which is now multivariate, but it's a PD for the score of the underlying density. And And these have the same property that if you plug your potential parameterization or your score parameterization into them and compute the residuals, then it's the same whether you apply it to the approximate or to the true. Okay, so we sort of motivated where we're going. We've come up with this approach for sort of measuring discrepancy between our approximation and true underlying Fokker-Planck equation. So what do we want to do with them? So two things. One is to prove that this residual getting small leads to convergence between the probability flow ODE and approximate SDE. And two is to then take this residual and use it as a sort of regularizer to try and push these distributions together a little bit. Okay, so the first one, without all of the assumptions, is essentially if we define the Fokker-Planck residual or the log Fokker-Planck residual by the L2 of the residual that I showed before, integrated from some time t to the final time horizon, then this residual being small implies that the Wasserstein-2 distance between the ODE and SDE distributions is also small. And I haven't written down what the C is, but C is obviously dependent delta, but it does depend on this integration time, so capital T minus T, and also the dimension of the problem. And you can show analogous results for the equations for the density or the score. And again, I won't go through the proof, but the idea behind the proof is to show that this residual getting small implies a strong score approximation, and a strong score approximation can allow you to bound, because we had an ODE formulation for our approximate SDE, we can compare that to our probability flow ODE, and this allows us to bound the distance between trajectories that these two things generate, which in turn lets us bound the Wasserstein distance. Okay. So the second thing we wanted to do is use it as a regularizer in training. So to do this, it's pretty straightforward. I take in my case, I use the denoiser score matching loss that I showed earlier, and I added on some weight times this Fokker-Planck residual and tested on these three test functions with different weightings, and then measured the Wasserstein distance between the generated samples empirically. This is what we got. So I guess focusing on this picture on the right, if you have no regularization, you get the image that I showed earlier, that's where there's clearly a difference. With just a little bit of regularization, we get much closer, although this clearly isn't perfect. With very strong regularization, these two things start to look very much like each other. But obviously there's a strong caveat here in that while the gap between these two has reduced significantly, the gap between this and this has increased significantly. So you're sort of paying the penalty of making your SDE samples worse, but pulling your ODE samples towards them. And this graph on the left is just showing the relationship between our sort of measured Wasserstein-2 distances here and the residuals. So we get the relationship suggested by this area. Okay, yeah, and so here are some tables that show a similar thing. So the top one shows what I just showed you in pictorial form. Basically, as you increase regularization, the ODE-SDE gap reduces. The second table is showing the difference between the ODE samples and the ground truth. So what we found here was that for mild regularization, you do see an improvement in the quality of samples that you get from the ODE. But for very heavy regularization, this improvement goes away because the distribution of both samplers gets worse. And for WSDE here, you find that regularization makes things monotonically worse. So if you want to sample from using an SDE, or you don't need deterministic mapping for whatever reason, then adding regularization of this type is not a good idea because it will just make your samples worse. Okay. So yeah, so there are further considerations. So obviously I've only played around with sort of these little models, and I use the potential parameterization. You can use score parameterization, and there is a piece of work that did this. But your PD, if your data dimension is very high, then this imposes a very high computational cost on having to evaluate this Fokker-Planck residual training. And you know, in practice, this isn't feasible. So in the piece of work that did this, they applied this Hutchinson trace estimator in order to calculate the second derivatives that they need. But on the results that they saw there were essentially consistent with ours. They didn't measure Wasserstein distances because they couldn't, but in terms of likelihood scores, they saw slight improvements for the ODEs, which were followed by worsening if you regularize too strongly. And for the SDE samples, they saw a monotonic decline in quality. So essentially the same as we saw, but we saw it by measuring Wasserstein distances to the true distribution. That's it. Thanks for listening.
Nice. Are there any questions? Yes, Robert. Oh, sorry.
You mentioned in the slide before this trace estimator. Wouldn't this be